Writing and solving applications. Let's first look at some financial models. For example, annual compound interest. So for example, find the amount that results when $300 is invested at 12% interest compounded annually for 10 years. So our original amount, our A sub 0, is $300. After 1 year, A sub 1 is 0.12, which is 12% as a decimal, times our original amount, 300, plus the original amount, which equals $336. After 2 years, we have 0.12 times 336 plus 336, which is $376.32. We could also have calculated this just directly as 1.12 times 336, because we had 1 times 336 plus the 0.12 times the 336. So 1 plus 0.12 is where we got the 1.12, because that also results in $376.32. After 3 years, we'll have 1.12 times 376.32, and that is $421.4784. Yes, I know I've not rounded to cents. I was going to wait to round things until the very end of the problem. So our formula to model this, A sub n, is equal to our starting value, our original value, 300, times, well, each term was multiplied by 1.12, so we will multiply 300 times 1.12 raised to the nth power. And we want to find A sub 10, so when n is 10. So A sub 10 equals 300 times 1.12 to the 10th power, which is approximately $931.75. So when we're dealing with money, we usually round to the nearest cent. So that's 2 places after the decimal. There is a formula for annual compound interest, and that formula is A equals P times 1 plus R raised to the T power, where A is the amount after T years, P is the principal or starting value, R is the interest rate as a decimal, and T is the number of years. So if we'd used this formula directly, we would have had A equals 300 times 1 plus 0.12 to the T power, or in our case, A equals 300 times 1.12 to the T power. And that is the same function we found. How long will it take the amount to grow to $1,500? So we had our function A equals 300 times 1.12 to the T power, and we want to know when it will grow to $1,500. So we will substitute $1,500 in for A. So now we have 1,500 equals 300 times 1.12 to the T power. We want to isolate our exponential expression, so we will divide both sides by 300. We get 1.12 to the T power equals 500. And now we will rewrite in log form the log base 1.12 of 500 equals T. So T is approximately equal to 54.837 years. Or we could round and say 55 years. Let's look at an example using depreciation. So for example, the cost of a new, there should be the word car in there. Let me add that word. The cost of a new car is $32,000. It appreciates at a rate of 15% per year. Write an equation to model this situation. So our original amount, a sub 0, is 32,000. After 1 year, we will have 32,000 minus 0.15 times 32,000, which is $27,200. We could also go directly as 1 minus 0.15 times the 32,000, or 0.85 times 32,000, because that also gives us our 27,200. After 2 years, we will multiply 0.85 times 27,200, and that is $23,120. After 3 years, we'll multiply 0.85 times 23,120, and that is $19,652. And that continues. Each time we are multiplying by 0.85 to get our next value. So a sub n equals our original value, 32,000, times the 0.85 that we continue to multiply by to the nth power. So this is an equation that models this situation. Now, when will its value decrease below $8,000? So let's take our model. A sub n equals 32,000 times 0.85 to the nth power. And we want to substitute 8,000 in for a sub n. So 8,000 equals 32,000 times 0.85 to the nth power. We want to isolate our exponential expression, so we will divide both sides by 32,000. We have 0.85 to the nth power equals 0.25, or 1/4. And now we will rewrite into log form. Log base 0.85 of 0.25 equals n, or n is approximately 8.53 years. So it will take 8.53 years for the car to decrease below $8,000. Let's look at another compound interest problem, but this time using continuous compound interest. And here we have a formula, A equals P times e to the RT. A is the amount after t years. P again is the principal or the starting amount. R is the annual interest rate as a decimal. T is years. E is the number E. And remember, I had said in an earlier video that Bernoulli discovered E, and it was while he was looking and exploring continuous compound interest. So for example, let's find the amount resulting from $400 invested at 7% compounded continuously after 3 years. So our formula says our amount will equal the principal, which is $400, times e to the 7% converted to a decimal is 0.07, times our time, which is 3 years, power. So our amount will be 400 times e to the 0.07 times 3 power, which is approximately equal to 493.471224, rounding to the nearest cent. We have $493.47. How long will it take for the amount to double to $800? So let's take our function, a equals 400 times e to the 0.07t, and we want our amount to be $800. So 800 equals 400 times e to the 0.07t. We want to isolate our exponential expression, so we will divide both sides by 400. We get e to the 0.07t equals 2. And now we will convert to log form. Remember, base e is the natural log, which is ln. So natural log of 2 equals 0.07t To get t by itself, we will divide both sides by 0.07, and t is approximately equal to 9.9 years. So it will take about 9.9 years for our investment to double to $800. Okay, let's look at some exponential growth or decay models. So we could write y equals c times e to the kt, where y is the amount after 2 years, c is the starting amount, k is the growth or decay rate, k is positive if it's a growth rate, k is negative if it's a decay rate, and t is the time in years. One thing to point out, this is a formula that we can use when we have continuous growth or decay. We will see another one that we can use when we have growth or decay each year. So for example, an insect population has a growth rate of 4%. If the starting population is 100 insects, how many would you expect after 50 days? And here we will use time units of days instead of years. So y equals our starting amount, 100, times e, our growth rate is 4% as a decimal, that is 0.04, and that's multiplied by t. And t in our case is 50 days. So y equals 100 times e to the 0.004 times 50, which means that we will have, after 50 days, about 738.9056,099 insects. But we can't really have part of an insect, so I will say after 50 days we will have 738 insects. When will the insect population exceed 2,000 insects? So let's take our model, y equals 100 times e to the 0.04t, and we want to substitute in 2,000 for y, so 2,000 equals 100 times e to the 0.04t. We want to isolate our exponential expression, and we can do that by dividing both sides by 100. E to the 0.04t equals 20, and now we will rewrite this in log form. The natural log of 20 equals 0.04t. Let's divide both sides by 0.04, and time equals the natural log of 20 divided by 0.04, which is approximately equal to 74.89330684, or approximately 75 days. Let's look at population growth with an annual growth rate. So, for example, the population of a town is estimated to increase by 12% each year. The population today is 24,000. Write an exponential function to model the situation. So a sub 0 is our original amount, 24,000. A sub 1 is 0.12 times 24,000 plus 24,000, which is 26,880. We could find this also by doing 1.12 times 24,000. After 2 years, we'll have 1.12 times 26,880, or we'll have 30,105.6 as a population. I am not going to round until the final answer. After 3 years, we will have 1.12 times 30,105.6, and that is 33,718.272. Each time we are multiplying by 1.12. So a sub n is our starting value, 24,000, times 1.12 to the nth power. Let's look at an example using half-life. There's a half-life formula that says n equals n sub 0 times 1/2 to the t divided by the half-life power, where n is the new amount, n sub 0 is our starting amount, t is the time, half-life is the time for half the amount of the substance to decay, and half comes from we are halving the amount each time. So for example, you have 100 grams of a substance that has a half-life of 20 days. How long will it take for you to have 20 grams remaining? So n sub 0 here is 100 grams. So after one time period, time period, we will have 1/2 of 100, which is 50 grams. And one time period is 20 days. That's how long it takes for the substance to decrease in its amount by 1/2. After 2 of these half-lives, we will have 1/2 times 50, or 25 grams. That's after 40 days. After 3 half-lives, we will have 1/2 of 25, which is 12.5 grams. That's technically after 60 days, since a half-life is 20 days. And so our general formula, n sub n, is our starting value, 100. And then each time we are multiplying our previous value by 1/2. So we will multiply by 1/2 to the nth power. So we have 20, we want to know how long it will take to have 20 grams remaining. So we will substitute 20 grams in for n sub n. So 20 equals 100 times 1/2 to the nth power. We need to isolate our exponential expression, and I can divide both sides by 100 to do that. So now we have 1/2 to the nth power equals 1/5. And rewriting this in log form, we have log base 1/2 of 1/5 equals n, which means it will take 2.3219 plus a little more half-lives for this to happen. Now, again, this is time periods or half-lives. So a time period is equal to actual time divided by half-life. So if our time periods are 2.321928 equals t, which we're trying to find, over our half-life of 20. So I can multiply both sides by 20 to solve for t, and t is about 46.439 years. Sorry, days. Because our half-life was in days. We're dealing with days. Now, let's use that half-life formula directly. N equals n sub 0 times 1/2 to the t over the half-life. So we could have put 20 in for n. Our starting amount was 100. And our half-life was 20. So we have 20 equals 100 times 1/2 to the t over 20th power. I can isolate my exponential expression by dividing both sides by 100. Now I have 1/2 to the t over 20th power equals 1/5. And I can rewrite this in log form. Log base 1/2 of 1/5 equals t over 20. And to solve for t, I will multiply both sides by 20. So t equals 20 times the log base 1/2 of 1/5. and that is approximately equal to 46.439 days, or 46 days. Let's look at one more example. This time we'll look at the Richter scale. And this is used when we're measuring or talking about earthquakes. So a Richter value is equal to the log of A over A sub 0, where A is the measure of the amplitude of the earthquake wave, and A sub 0 is the amplitude of the smallest detectable wave. So for example, an earthquake is measured with a wave amplitude A equals 0.312 centimeters, while the smallest detectable wave, A sub 0, is measured at 0.0001 centimeters. What is the magnitude of this earthquake using the Richter scale? And we're going to round to the nearest tenth. So R equals the log of A over A sub 0. So the log of A is 0.312. A sub 0 is 0.0001. So the log of 0.312 divided by 0.0001 is approximately equal to 3.5 on the Richter scale.